in AMC12 and also a lot of other mathematical competitions. Oftentimes, the hardest geometry problem in a test is related to circles. And what is oftentimes treated as the most important thing in circles is cyclic quadrilaterals. And the reason of which is that cyclic quadrilaterals and circles in general, there are many nuances as to the angles, lengths, and the possible auxiliary lines, the relationship between lines. Sometimes discovering these patterns can prove quite difficult, and that is exactly the reason why circles are the most hardest thing in geometry. Yet today we will be diving into circles, and I will teach you everything about circles that you need to know, and we'll take a look at a few difficult problems to give ourselves a better understanding of what is going on. Let's dive in immediately. And this problem is today's warm-up problem. This is under the context of circles, but it is not exactly a geometry problem. But anyhow, it is an interesting problem and a difficult one, so let's take a look. Essentially, in this circle, there are three different types of length, and that is, in a sense, a key observation of this problem. First of all, it's when two adjacent points are connected. Then there can be one single point between 2 points, and also like that, 2 points between them. And when you draw any other line, it is already covered in these three different lengths. And you can count this yourself. There are 7 such segments for each type. Well, after locating the center of the circle, we can connect the radiuses, and then this forms a triangle. To find the length, then we can use the law of cosines. And then applying the same process to each of them, you would find that the three lengths, let's call A, B, C, have the characteristics a squared equals 2 minus 2 times cosine 2 pi over 7. B squared is then 4 pi over 7, and then c squared is 2 minus 2 times cosine 6 pi over 7. And that essentially is the geometry part of this problem. Now, the rest is algebra. We have already covered a similar problem, and that's exactly why I say this is a warm-up problem for you guys. So try to do it yourself now. Let's take a look together. First of all, since we're asked the fourth degree values, then let's square it. A to the fourth degree then is 4 times cosine squared of 2 pi over 7 minus 8 times cosine 2 pi over 7 plus 4. And then b to the fourth degree is 4 times cosine squared of 4 pi over 7 minus 8 times cosine 4 pi over 7 plus 4. C to the fourth degree is 4 times cosine squared 6 pi over 7 minus 8 times cosine 6 pi over 7 plus 4. Then our desired answer is then 7 times a to the fourth degree plus b to the fourth degree plus c to the fourth degree, which is exactly equal to 28 because we can factor out a 4 out of everything, multiplied by, first of all, cosine squared of 2 pi plus 4 pi plus 6 pi minus 2 times cosine 2 pi plus cosine 4 pi plus cosine 6 pi. And then finally, we add the constant here, which is simply 3. Next, let's find the values of these two equations. And last time we have already motivated you guys to understand that here we're using complex numbers, especially the unit roots of those complex numbers. Suppose z is equal to e to the 2 over 7th times pi times I power. And in this case, this is the 7th root of unity. And we can represent cosine 2 pi over 7 as z plus z to the 6th degree divided by 2 cosine 4 pi over 7 to the z squared plus z to the 5th degree over 7 over 2. And then cosine 6 pi is equal to the following values. And then we can square them. Squaring them still leaves very clean expressions. That's the reason we use complex numbers. Now, remember, the sum of the root of unity, the 7th root of unity, which essentially is 1 plus z plus all the way up to z to the 6th degree, it is 0. So if we move the 1 over here to the right, then it is negative 1. So in the above expression, since you're trying to find the sum, then the sum of these terms is exactly equal to negative 1 over 2. And then the sum of these terms should then be equal to negative 1 plus 6 over 4. Thus, with that, our desired result is equal to 28 times 5 over 4 plus 4. and this is equal to 21 over 4. So our answer in the end is 147, and we are done. So this is a starting example on circles, and you can see how circles are beautiful because when you rotate it around its center, it doesn't change. So it has a lot of interesting features. Yet it is not the main topic of today. We are going to dive into even more interesting stuff. So let's not waste time and move on to the next part. Now we're going to study some theory. First, let's get a circle ready. Next, suppose we have a few points, A, B, C, D. Let's connect every possible segment between these points, and let's see what patterns we can find. So first of all, let's take the center of the circle. It never really hurts. In this case, I don't really have an accurate graph, but let's just say the center is located somewhere here. I don't really want it to be on any given segment, so let's put it slightly aside from segment AC. In this case, when we connect these lines, we have the famous identity that the central angle is double its angle on the circle. And similarly, it is also equal to twice angle ACD. That means angle ABD is equal to ACD. So important property. And also, since the arc ABC is equal to 2 pi minus the arc DC. That means the angle ABC is equal to 180 degrees minus the angle ABC. And of course, these are the basic angle facts. And in fact, given any of these two, for a general quadrilateral, you can prove that the quadrilateral is exactly on a circle. Let's take this for an example, and you will prove this one yourself. Let's remove the circle for now, and suppose we're trying to prove that this thing is a cyclic quadrilateral given ABD is equal to ACD. First, let's take the circumcircle of ABD, which we craftily avoid point C. And this is looking like a goose egg, but just take it. Now, of course, this passes through D. Oh my god, this thing looks so ugly. Now, let's say this intersection point is C prime. Then we can connect these points. So we know that ABD is equal to ACD. But we know also that ACD is equal to AC prime D minus CAC prime. And since both these values are equal to the angle ABD, that means this is 0. So C and C prime are exactly the same points. Thus, we can prove that C must be on the circumcircle of ABD. And we're done. Now, there's some more interesting things here related to lengths. And the reason I say so is, remember, we already have one pair of equal angles, and this, of course, is definitely equal. And suppose the intersection here is P. Then we have triangle BPA is similar to triangle CPD. And what this gives us is BP over AP is equal to CP over DP. That means BP multiplied by DP is equal to AP multiplied by CP. In fact, what it means is given any line passing through P, suppose it intersects at x and y, then px times py is a constant value, given p is a fixed point. So we can assign this value a name, which we call the power of this point, or power, short for power. And we have the center O. Of course, in theory, you should include the radius as well. So perhaps you can write it like this. Of the point P is fixed. Can we assign it a value that really makes a lot of sense? Of course, yes. Because suppose the line here is not any random line. It is passing through the center of the circle. Then we have the power of the point P is equal to the radius minus OP multiplied by the radius plus OP. So this is the definition of the power of the point, or also r squared minus OP squared. In fact, when the point P moves out onto the circle itself, then this value is 0. And when it moves even further, then this value is negative. However, mathematicians, they do not begin with what we have done. So they would rather prefer when a point is outside the circle, then the power is positive. So the actual definition is OP squared minus R squared. So we should put a negative sign onto everything. And this is the official definition of the power of the point. Also, there's something interesting called the radical axis of two circles. But it is not really of that much importance. You can search it yourself. It is essentially a line where the points they have the same power relative to two circles. Then the set of all such points form the radical axis. And perhaps you noticed another potential similarity. For example, we have these two angles are the same. Then that means it is possible for us to construct a similar triangle. Admittedly, this is not very straightforward if you're trying to discover the theorem yourself, but it is just something possible that you might try when you see two angles are already the same. So you can construct another angle such that it actually forms something interesting. In this case, let's take these two angles. Let's call this point Q. Then we have a new similarity that we constructed ourselves. In this case, what we can gain here is AQ over CD is equal to AB over BD. That means AQ is equal to AB times CD over BD. Similarly, in fact, you can discover that CQ is equal to BC over AD divided by B. So that means AC is equal to AB multiplied by CD plus BC multiplied by AD over BD, which we can write over here. So this becomes AC multiplied by BD. What we have here is the famous Ptolemy's theorem. And let's take a look at what this geometrically means. It is saying that when you multiply AB by CD, the opposite side lengths, and plus BC multiplied by AD, it is exactly equal to AC multiplied by BD, which is a really useful expression for the diagonals in the cyclic quadrilateral. So in hindsight, suppose we're trying to represent AC using other side lengths that are already given, then taking a point on AC and constructing a similar triangle makes a lot more sense. If you came up thinking about this, then congrats, you're really built for a mathematician. But if you didn't think of this yourself, it's okay. Sometimes mathematical discovery really requires some luck and some inspiration. But now I would like to mention something interesting, which is recall that previously we represented the area of triangle ABC using the Heron's formula, which resembles something like this. Now, this only includes side lengths. I'm curious to ask if you can solve this yourself. What is ABCD, the area of this cyclic quadrilateral, in terms of the side lengths only? No angles are allowed. Try it yourself. And a hint, sine theta is equal to sine 180 degrees minus theta. And this is exactly the reason why cyclic quadrilaterals are special, because they have this pair of angles that adds up to 180 degrees. So try to derive it yourself. The answer is, in fact, very similar. Finally, an even more interesting problem. Suppose ABCD is not cyclic anymore. Do you have any ideas on how to find its area anyhow? Think about it yourself. This is not really seriously covered in modern AMC12, so you don't really need to worry about this. But if you're interested, you can try to solve this yourself. This is called the Brahmagupta's formula. Interesting name. Now let's take a look at some problems. First of all, we are given a problem with some random looking angles and lengths. But let's draw this. A good graph is the key pathway to solving a geometry problem. We are given BC is equal to 6 and AD is equal to 4. The angle BAC is 70 degrees and ADB is 40. What do we know here? Using the characteristic of circles, we know this is 40 degrees, and that means this is 70 degrees. So BC is equal to AC, AC is equal to 6, and we are done. A good graph is all we need to solve this easy problem. Next, something a little more interesting. We have an isosceles right triangle, ABC. AB is equal to AC, which is equal to 3. And we also know M is the midpoint. So there are some points, AI and AE, that satisfies AIME is a cyclic quadrilateral. We are given the area, which is 2, and we're supposed to find CI. So it is pretty obvious that since it is a cyclic quadrilateral, if this is 90 degrees, then this should also be 90 degrees. And then that means MI is equal to ME, which is equal to 2. Also, remember, AB is equal to 3. So when we connect AM, we know that the length here is, in fact, 3 over 2 times square root of 2. And of course, now you can set some variables. If AE is equal to x, then CI is also equal to x. AI then is 3 minus x. And of course, you also have EI, which is equal to 2 times square root of 2. So basically, every length is represented in this cyclic quadrilateral. And since you already know the diagonals, you might be tempted to use the Ptolemy's theorem here, because you can just create a system of equations that's really easy to create, and you can solve. But of course, since you already know x and 3 minus x, and you already know the hypotenuse, then that means it won't be very hard for you to solve simply using the Pythagorean theorem. And as promised, it is time to tackle some difficult, challenging problems. The first one you're seeing is from AMC12 Set B Problem 24, a difficult geometry problem. Let's first draw the diagram by hand because it is honestly a really important part. So first of all, we have a parallelogram with area 15, ABCD with area 15. PQ are the projections of A and C respectively onto the line BD. Points R and S are the projections of B and D onto the line AC. PQ is 6, RS is 8, and we are to find the length of BD. But it is absolutely off. But some more experimentation will give you a better diagram, which you are currently seeing here. So what can you gain from this graph? What inspiration do you have? Since today we're talking about cyclic quadrilaterals, you might be tempted to find a cyclic quadrilateral. And if you're lucky, the one that you will detect is exactly this one. We have APRB is concyclic. Let's analyze it. Remember, PQ is equal to 6, so that means PM, here M is the midpoint of PQ, and also BD is 3. Similarly, MS is 4. Then we can set some variables. Since actually the accurate graph satisfies that it looks more like this. M is exactly the intersection of AR and BP. That means we can apply power of a point because the 4 here, R is also equal to MS. So that means if we set this to be 3x, then this is 4x. So MB is equal to 4x, AM is equal to 3x. And essentially, BD is simply 8x, and we just have to solve for x. Okay, and then now we can go back to analyzing which constraints we haven't used yet. And one of those is that the area of ABCD is exactly 15. So let's solve this because BD is 8x, that is known, and then AP is 3 times square root of x squared minus 1. This is equal to 15. Here, we can square both sides. That means 64x squared multiplied by 9 times x squared minus 1 is equal to 205. Now let a equals to x squared. Then we have 64 multiplied by 9a minus 1 is equal to 225. Some simplification will give you the result a is equal to 4 plus or minus 40 over 8. Remember, this must be positive, so the negative sign can't be taken. That means x squared is simply equal to 4 plus square root of 41 over 8. Since we're only asked BD squared, then all we need is 4x squared. Plugging it in gives 64x squared is in fact equal to 32 plus 8 times square root of 41, and we are done. As you can see, it is not very difficult. Basically, we observed there is 4 points that is concyclic, and then we moved on to create a representation using power of a point, and then finally, we just use the constraint of the area to solve, and it isn't really that hard. So if we are not talking about cyclic quadrilaterals today, you might not have discovered that APRB is concyclic. However, when you are tackling geometry problems, a good habit is to go through what you know and try to filter through those things that you haven't tried yet, and then you can try them one by one. Because sometimes pure geometry approach to geometrical problems is going to be requiring a bit of inspiration, some auxiliary lines, some discovery, and it is not always easy. I hope you got a better understanding. Let's move on to the next problem. Now, let's tackle our second and last challenge problem. This one is from 2017, set A, problem 24 again. So as you can see, a lot of problem 24s are difficult cyclic quadrilateral geometry problems. So take a moment to read the problem and draw the diagram yourself. I will show you directly the diagram when you finish reading the problem to save some time. Here we go. Let's just break this thing down step by step. First of all, it is quite obvious that since we have some similarities, for instance, we have AXD is similar to EXY because of the parallel lines. That means dx over xy is equal to 9 over 16. And then similarly, you also have ACX and EFX. So we also have AX over XE is equal to DX over XY is equal to 9 over 16. So that also means XF over CX is 16 over 9. So since the problem asks XF and XG, which doesn't seem like something very natural, you can then convert XF and XG to XG and XC. So it's simply 16 over 9 times CX times x, which also happens to be dx times xb. So all there is left at this point is finding BD, because you know the ratio of dx to xb. So all you need is finding BD. What can we do here? We would like to apply Ptolemy's theorem, but let's see if we can. AB is equal to 3, and BC 2, CD 6, AD 8. Given these constraints, we can find BD multiplied by AC. But it is not directly clear how we can go from knowing BD multiplied by AC to finding the exact value of BD. So let's try something different, which is, since we're trying to find side length, then naturally we should consider the law of cosines. Suppose this is theta, then this is 180 degrees minus theta. So by the law of cosines, BD squared can be simultaneously represented by the following equations. And this term here can be written as plus 24 multiplied by cosine angle of BD. And then equating these two values gives you the result, because it is pretty simple to solve for BAD here. And then consequently, you can find BD. BD is simply square root of 51, or BD squared is 51. And then you can just plug it in and you have the result. The answer for reference is 17. Well, in fact, this is pretty inspiring because it shows you that using the law of cosine, you can arrive at something similar to the Ptolemy's theorem. So you can try yourself and see if you can prove it. Because in this case, given these four values, A, B, B, C, C, D, A, D, then you can use the law of cosines to solve for the angles and also BD and similarly AC. So you're able to represent BD and AC using the side lengths without the angles. So simplifying it down, you should have the same result as Ptolemy's theorem, only it's going to be a bit more algebraic heavy. However, that's all for today. As you can see, if we know the systematic way to approach geometry problems, then it's going to be a no-brainer. At least this seems a lot easier than those hardest algebra problems. But it really takes some training to get an understanding of how to approach pure geometry problems. However, we'll be leaving this realm of geometry in the next video, and we'll be entering analytic geometry, which is fun stuff as well, and is what is actually emphasized in geometry at modern age. So to end today's video, I have some homework for you. First, a relatively basic problem related to circles and Ptolemy's theorem or trigonometry. You can decide what to use. There's no right or wrong to that. And then here, it is an interesting problem related with isosceles trapezoids. And hints are, first, consider what is special about an isosceles trapezoid. And then, secondly, it is that you would rather like to construct another trapezoid with known side lengths, because currently we know nothing about the side lengths, but can you construct one? This is a little more difficult, and it might require some interesting things. So a final homework is what I've already mentioned. Consider the area of a quadrilateral. What is special about a cyclic quadrilateral? And can you compare it with other more general quadrilaterals? That is an interesting thinking problem, and I would like you to consider it. That's all for today. I am really looking forward to the next two sessions because I think it is two of the best videos I have in this course. So you can subscribe if you're looking forward to it as well, just like me, and then I will meet you in 2 days. Bye.